Bismillahirrahmanirrahim. Assalamu alaikum dear students, welcome back in lecture 01 example 03. Student, as you see in 002, in example 02, we have started this example, right? And in this example basically we review this example for case number 1. Today we will review this case number 2, so let's start the solution. In this example, as you see here, that we have given 6 number 10 bar. So we need to find out the area of steel. But before starting the review problem, I have already mentioned that we have to use the assumption that, let's say, Fs equals to Fy. This means what? This means that, let's say, we are assuming that the steel is yielding, right? So now the width of the section is given, right? Let me write down the data. We have 12 inches. The depth is given, that is 15 inches. Remember, in this case we are assuming that the steel is placed in one layer, so that why, due to, we can say d equals to dt. And similarly we will use that strain in steel will be equals to strain epsilon t. Now Fc prime is given, that is 3000, psi are 3k psi, and Fy is given, that is 40,000, psi are 40k psi. And what we have to determine, we have to find out the moment capacity, that is flexure strength Mn. We have to find out this, right? So this is all about the data, and now let's start the example. So what we need, the first step, as I already mentioned, that we need to find out A. So A, from the equation as Fy 0.85 Fc prime into B. We know all data, right? Just plug all the data right in this equation. What we got, the value of A is 9.92 inches, right? So this one will be the value of A. Now again, what we need the value of C, right? And the value of C will be determined by A divided by beta 1, and make sure beta 1 value, right? As we know that Fc prime value is less than 4000 psi, right? Psi. So that why our beta 1 value will be 0.85, right? Beta 1 ranges from 0.65 to 0.85. So that why, using that value, A divided by beta 1, and you will see the value that 9 point, from here, from my calculation which I have do right here, 9.92 divided by 0.85, I got 11.67. so from this I write down here 11.67 inches. This is my value of C. So I need to calculate epsilon s, and epsilon s will be equals to epsilon t. From proportionality we can write down d minus c divided by epsilon u. Now from this, if you use this relationship and plug all the value in calculator, you will find the results with 0.000856. This is interesting, 856. Now here you can see that if you calculate the value of epsilon y, right? If we calculate the value of epsilon y, that is nothing Fy divided by modulus elasticity of steel. We know this is 40 and this is 29,000. What we got from this 0.138. So 138. Now if we compare these two values, right, we have to compare this epsilon s with epsilon y. We clearly see that epsilon s is well below the value of epsilon y. Now this means what? This means that the assumption which we used in the initial stage, that Fs equals to Fy, is wrong. This suggests that the steel is not yielding. In all the previous example, if you see, epsilon s is more than epsilon y. That's why we can say this assumption is right. But here you can see the strain value is less than the yielding strain. So that's why the stress in the steel not reaching to the yielding stress. So that's why this assumption is wrong. Now from this, what we can determine, we can say that the section is under compression. The steel is not yielding, so the section is a compression section, right? This section is a compression section. And we know the graph right here. From the graph we can say this is my epsilon t value and here is my graph, right? So now we are in this region. This is the compression region, and the p value will be 0.65, right? And this here is the epsilon t value 0.002, right? Now now we have to find out the value of A again. Because our assumption is wrong, we determine the value of A on the basis of this assumption, right? We see here we are using the yielding stress of the steel. So that why assumption is wrong. So we can say that the value of A is wrong. This value will no more work. So we have to find out this C is wrong, right? We have to find out again these values for an over-reinforced section. Now this is the case I have already explained in lecture 01 in part 06, I think so. I have already discussed an over-reinforced section, right? Over-reinforced section. How to analyze an over-reinforced section. In that section, basically you see I have derived an equation, right? If you remember that equation and if you watch that lecture, because in 05 we discussed an under-reinforced section, but in 06 we derived an equation for an over-reinforced section, that is Ku square root equals to m times rho plus m times rho divided by 2 square, then minus m times rho divided by 2. So here we will use this equation. We know that Ku is what? Ku is nothing, it is equals to C divided by D, right? C divided by D. And we also know the value of m, right? When we are deriving this equation, we assume the m value, that is Es modulus of elasticity of steel times strain in concrete divided by 0.85 Fc prime fc prime into beta 1, right? So now we will proceed with this equation, right? We will use this equation. So we know all the value of all these values, right? We know es, that is 29,000 ksi, epsilon u, we know this 0.003, beta 1 0.85, and fc prime is 3 ksi. So if you plug all the values and use the calculator, what we got here, the value of m will be 40.13, right? Let me show you the values. 29 ksi times 0.003 divided by 0.85 times 0.85 divided by fc prime, that is 3, right? So from this you will got this result, right? Now we will use that equation and we will determine the value of ku, right? So if you plug all the value here, rho is in question. Let me determine the value of rho. We know rho is the area of steel ratio. This is the steel ratio, means area of steel divided by the section area. So from this we got rho value, that is 0.0422, right? 0.0422. This one will be the value of rho. So we have rho here, right? We have m value right here. So you need to plug all the value in this equation. What you got from this equation, you got the value of ku, that is 0.705. This one will be the value of ku if you use that equation, right? So now we are able to find out the value of c and a, right? We know the value of ku is nothing, it is equals to c divided by d. From this we will find out the value of c, that is ku times d, and if you insert this value 0.705 here and d is 15 inches, we will find out the value of c, that is 10.587 inches. So from this we can easily find the value of a. A is nothing, it is just some fractional distance of c. So beta 1 times c, we know beta 1 is 0.85 times c value. So if you do this calculation, you will find a value, that is 9 inches. Now this is 9 inches. So now we are able to find out the value of mn. Okay, we can find out the value of mn, that is a is fy into d minus a over 2. So we know all the values. We know as, we know fy, we know d, we know a, as we determine here this value, right? This one. So 9 inches divided by 2, and here it is important that the value, because as we see the section is in a compression region, from the graph it is clear the section is in the compression region here, right? In this zone the section is under compression, so that why the p value will be 0.65, right? And if we multiply this p value with the value which we determined from this equation, the final value of m in will be the final value will be 156.5 0.63 feet, right? This one will be the final value. So once we got the value of C and A, now we can easily find out the value of Mn. But here the case is different. Remember, we have to again recalculate the value of epsilon s, right? We will again calculate the value of epsilon s, that is d minus c divided by c, right? From this times 0.003. So this time you will find the value of epsilon s. Let me recalculate this value. What I got here in my calculator, that is 0.00125, right? Now this time the strain value will be this one. From this, remember, as we know that f is not equals to Fy, so what will be the value of the stress in the steel? We will calculate this from the Hooke law, that is modulus of elasticity times strain in the steel. We know this is 29,000 and we have to multiply with this. What I got here, multiply the strain value by 29,000, I got here 36.34. Now this is important. This is important, that is, this is in KSI. Now you see this is well below than the 60 KSI, which is the yield stress of the steel. This is, sorry, this is not the 60 KSI steel, this is 40 KSI steel, sorry, right? So this is below than that specified value, right? So now if you want to find out the value of Mn, so you have to use this Fs, not Fy, right? So Mn equals to phi times Fs times area of steel into d minus a over 2, right? So here you must remember that this is a compression control section. This is a compression control section, so that why we will use P equals to 0.65, right? So here we will plug all the values. 0.65, Fs is 36.34 into area of steel. Noting here, area of steel is what we got here. I think so we don't yet calculate the area of steel here, although you can easily calculate the area of steel as we have 6 number 10 bar, so we can easily find out the area of steel is 6 times 10 divided by 9 square. From this you will got the value of AS, which is 7. I think so 7.59 square inches, right? So 7.59 square inches. So here we have the value of AS, that is 7.59 into d minus a over 2, that is 15 minus a over 2 is 9 inches divided by 2, and we have to divide it by 12, right? This value is in KSI, so we don't need to divide it by 1000, but we need to divide it by 12 to convert it into feet. What we got here, this is 156.63 feet cap. This will be the design flexure strength of the section. Now let me share you some important things right here, that here you can see we calculate the value of fs, right? We calculate the value of it is, that is 36.34 ksi. We can also, if you don't want to calculate the value of fs, you can calculate the value of mn by using the equation c times lever arm, that is d minus a over 2, right? A over 2, because we know from the analysis as we done in the previous section that, let's say we have a section right here, we have a rectangular stress block here, and we have compression right here, that is C, and we have tension right here, that is T. The center to center distance between these two is d minus a over 2, because this is the star fiber, this distance is a over 2, this depth of concrete block, stress block is a, right? So already we calculated a, we can find out a over 2, and the total effective depth is, this is 15 inches, this is d. So the moment of resistance mr or mn, we equate this with mn, it can be c times lever arm d minus a over 2, or it can be found out by t times b minus a over 2, and we know t is equal to ASFS. So that's why we are using this equilibrium equation, and we will calculate the value of C. We know the C value, that is 0.85 FC prime into B into A into D minus A over 2. Now we know the value of B, that is 12 inches. We know the A, that is 9 inches. We calculated, and if you multiply this with the reduction factor, that is 0.65, right? So from this we will find out the same result, 156.63 kf feet. So this is the another way of doing such calculation in the case of an over reinforced section, although you can also do this calculation in the case of the under reinforced section, right? So this ends up this example. You see how to analyze an over reinforced section, right? When you have to face such a section, then this is the way that how to analyze such section. Thank you for watching. See you in next.